Okay, so this is the fourth video now on second order differential equations, and this one is nothing new. We're just going to show a few more examples of how to work out the complementary function and the particular integral for some different second order differential equations. I'm focusing mainly on the particular integral aspect of it. That was the subject of last video. So here we're sticking with this very familiar left hand side, just because to find the complementary function. For this particular equation, we know what it is because we just let the left-hand side equal 0. And we solved this one, I think, in the second video. And we worked out then that it was equal to a e to the minus 2x and b e to the 3x, because the roots were minus 2 and 3 for the auxiliary equation. The reason we're doing that one is so we can get on with working out the particular integral. So we've got to try and choose a correct particular integral for this function here. So we look at it, we ignore the 5. The 5 is not that important right now. It's the 2 in front of the x that determines the particular integral. So here we'll be letting it equal to y, so is equal to lambda e to the 2x. So we always have this unknown multiple at the front, but it's the 2x that we use to get the right starting point. And we differentiate it, and that means that we end up with this, and we differentiate again. Again, differential of e to 2x is the same, but you times by differential of bracket each time. So these 2's keep popping out. And you see where the 2x needs to be there so that when we plug these things in, we've got a chance of it equaling e to the 2x. So we now plug these things back into here. So d2y dx squared is for lambda e to the 2x. Then we're taking away dy dx. Then we're taking away 6 lots of y. And that's all equal to 5 e to the 2x. And when we're doing the particular integral, it's actually equal to the function it is. It's only the complementary function where you stick it equal to 0 for some weird reason. Now we're going to expand this side. So we've got 4 lambda minus 2 lambda minus 6 lambda, and that's all times by e to the 2x. And that's equal to 5 e to the 2x. And we can see that this bit here must equal this bit here. In fact, how many lambda have I got here? I've got 4 minus 2, I've got 2 minus 8 minus 4 lambda, would you know that? So minus 4 lambda must be equal to 5 there. Just double check that. Yeah, it looks right, doesn't it? So that means that lambda must be minus 5 over 4. We divide by minus 4. Which is great, because that tells me then that for this particular question here, my particular integral is minus 5 over 4, that's the lambda bit, e to the 2x, which is good. And then to make it general, we just add on the a e to the minus 2x and the b e to the 3x, and we're done. Let's do another one. We'll use the same left-hand side. Just it saves us time with the complementary function. And we'll look at another function on this hand side. So let's do something like 3x squared. So we start the same way. We work out the complementary function, but we've done that already there. So let's just go on to work out what the particular integral is. We're trying to find the general solution for this thing here. So we've got to try and choose the right y. So we look here and go, oh, this is a quadratic. So it means we choose a general quadratic, not just an x squared term, but the whole thing with 3 unknowns. Differentiate it. See, as differentiated, this becomes a lower power, and this becomes a lower power. And then differentiate again, and it becomes a lower power again. See, these terms here again allow us to have some chances to cancel out those lower powers. If we just had this one, we'd be left over these extra lambdas that we don't want, and these things allow us to get rid of them. Now we plug this back into this equation, so d2y dx squared is 2 lambda. Then minus dy dx, which is 2 lambda x plus mu. and then minus 6 lots of lambda x squared plus mu x plus nu, and that's all equal to 3x squared. Let's just try and expand and group together the different terms. So we've got minus 6 lambda x squared. The x terms, we've got minus 2 lambdas there, and over here we've got minus 6 mu's. That's the x terms, and there's 3 constant terms. We've got 2 lambda, there, minus mu, and minus 6 mu, and that's all equal to 3x squared. Again, we compare coefficients. So we can see the x squared coefficient, the minus 6 lambda, must be 3. And then this coefficient, minus 2 lambda minus 6 mu, must be 0 because there's no x term. And the constant must also be equal to 0 because there's no constant on the right hand side. And these are quite easy to solve because you can solve them one after another. So this one here tells us that lambda is minus a half. We can use that in here. So minus a half times minus 2 is 1. Minus 6 mu equals 0. Telling us that mu is equal to 1/6. And then plug both those in there. I've got minus a half times 2, which is minus 1. Minus a sixth minus 6 mu equals 0. Oh, so that's minus 7/6. So we end up with minus 7/6 is equal to 6 nu, which means we've got minus 7 over 36 is nu, unless I'm mistaken with my math. And then we can plug it all back in to get our particular integrals being the lambda, which is minus a half x squared, the mu, which is a sixth x, and the nu, which is minus 7/36. Yep, that's all in there nicely. And then to make it the general solution, we just add on the complementary function, sort of plus c for second order differential equations, if you like. Oh, that's meant to be an X just there, but I'm sort of losing control of pen at the bottom of the page. Okay, there's 2 examples for you how you can use the particular integrals we were talking about in the last video in practice to work out what the actual lambda or lambda mu and nu terms are, and therefore get you your general solutions to different differential equations. Plenty of practice to do that now. Good luck.